Electricity. Everything you need to know about electricity. In grade 10, you had a look at Ohm's law. Ohm's law, V equals I times R. Volts equals current times the resistance. And you know that you can go and rewrite this formula in many different ways, and oftentimes we use a triangle where we have V here at the top, I, and R. This is just an easy way for us to go and rewrite the formula. If you want to calculate current, it's voltage divided by resistance. If you want to go and calculate resistance, it's voltage divided by current. So we can use Ohm's law. And this specific Ohm's law that you are going to do with me today, we are going to apply when we have ohmic conductors. So in today's lesson, we're going to have a look at a few new things, ohmic and non-ohmic conductors being one of them. So when we start off also, let's go and have a look at the relationship between voltage and resistance and current. If you were to go and draw a graph for this specific example, R equals V over I. We know that in grade 10 we saw that as the voltage increases, our current also increased. And we saw that basically voltage was directly proportional to current in grade 10. We never had any other example. So for example, if you have nichrome wire, we know that this is true, and it is called an ohmic conductor. Ohm's law, by the way, can be summarized as the following. Ohm's law, the current flowing through a resistor is directly proportional to the potential difference across the resistor, provided the temperature stays constant. But we all know that the temperature doesn't always stay constant when you have a resistor. If you've ever been as unfortunate to perhaps touch a light bulb when it's switched on, you might have lost your fingerprints. And that is because sometimes we know that resistors can be non-ohmic. And then when we go and draw voltage versus current, we get a line that looks like this. Now, how do we go and calculate the resistance when it looks like this? We can go and draw a tangent. And when we draw a tangent, we can go and we can calculate the resistance. Remember, the steeper the tangent, the higher the resistance. And this is true, for example, in LED lights. It's true for many different appliances that use resistors. So just be aware of the fact that we have ohmic conductors and non-ohmic conductors. I'm going to introduce you to a couple of new formulae today as well, and something learners often struggle with. If you have a look at this formula, Q equals I times T. Q by now you might recognize from previous sections of work. Electrostatics, we looked at charge, electromagnetism. So remember, we are not dealing with static electricity now. We are talking about flow of charge here. So we know that Q is a symbol for charge. Q is a symbol for charge. It's measured in Coulomb. And we know that I is a symbol for current. It's measured in ampere. And T is a symbol for time. It's measured in seconds. So we can basically go and say charge measured in Coulomb is going to be equal to the amount of amperes multiplied by the time. So the unit of a charge here is Coulomb. 1 Coulomb is the amount of charge passing through a point in a circuit in 1 second when a current of 1 ampere flows in that circuit. Now, something that learners find a little bit confusing is the concept of charge. So let's talk about it quickly. Charge is actually a positive or negative. That is what a charge is. But now, just to give you an idea, if you go and you look at an electron, on your information sheet with every exam or perhaps at the back of your workbook, you will find the charge on an electron is going to be equal to the negative. That negative just means an electron is negative. 1,6 times 10 to the power negative 19 Coulomb. So to give you an idea, in 1 Coulomb of charge, we have 6,25 times 10 to the power 18 electrons. That's a lot. So if you have 1 Coulomb of charge, you actually have billions of electrons in 1 Coulomb of charge. Each and every electron carries a small amount of charge. When we have the flow of charge, we have current. So when we combine all of this, we can go and rewrite the formula and say that current is going to be equal to the amount of charge per second, or I equals Q over T. In a series circuit, we also know that the current is the same everywhere, and we know in a parallel circuit that the current divides among the parallel branches of that circuit. We're also going to look at the new formula for voltage. Voltage equals work measured in joule. This is actually energy divided by charge. So we can basically say that the potential difference, or volts, indicates the work done by electrons as they move through a cell or a resistor. So remember, some of the energy of the electrons will be converted to light energy, some of it will be converted to heat energy. Potential difference between 2 points in a circuit is the work that must be done to move 1 coulomb of charge from one point to the other. So this is a new formula for you that you have never seen before, and we're also going to now branch out and go and explore how we can use these various formulae. When we did Faraday's law, we touched on something called EMF. Now, EMF basically is the total amount of energy that a battery can supply. It is measured in volts. So if you go and you buy a cell, we sometimes just call it a battery, we know that there will be a measurement actually written on the cell or battery, 3 volt or 9 volt or whatever the case is. And that refers to the EMF. Now when we go and we connect conducting wires perhaps, and let's say a little resistor or a light bulb to this circuit, then when we switch this circuit on, let's imagine there's a switch, we will see that when the circuit is closed and current is flowing, if we have a voltmeter connected over this cell or battery, and let's say it had a reading of 3 volts, now all of a sudden that 3 volt reading, which was the EMF, changes to, let's say, 2,8 volt. The reason for this is because the external circuit, meaning everything connected on the outside of the cell, now will take up 2,8 volts. What I want you to see here is that there is actually something called internal voltage. The full 3 volts will not be delivered to this circuit. And as long as you are aware of that for now, it's going to be good enough. So external potential difference is also measured with a voltmeter. Remember that you can also connect that voltmeter over this resistor, and it will also give you the same 2,8 volt reading. These are some of the basics that you need to know to be able to move forward in grade 11. So we have these 3 formulae. The one from grade 10, which is Ohm's law. We looked at ohmic conductors and non-ohmic conductors. And then also we looked at these 2 formulae over here, where we say current is the amount of charge per second, and volts can be defined as the energy needed to move 1 coulomb of charge from one point to the next. We're going to use these formulae interchangeably. Remember, they will always be given to you on your formula sheet. Can we have a look at some examples then?